In this video, we are going to learn about the functions of the liver, its structure and its functions. So, learning objectives are: list the functions of the liver, describe the composition and functions of bile, describe the enterohepatic circulation, describe the types of jaundice. Before moving on to this topic, let's learn some major terms associated with like jargons. First is the bilirubin, a pigment that is formed from the heme ring of hemoglobin on destruction of RBC. Then gluconeogenesis, the process of formation of glucose by the liver from non-carbohydrate sources such as amino acids and glycerol portion of fats. Jaundice is a yellowish discoloration of the skin and deeper tissues. Then Kupffer cells, Kupffer cells. Kupffer cells, liver macrophages that line the sinusoids and are capable of phagocytizing bacteria and other foreign matter. Then liver lobule, the basic functional unit of the liver. Although the liver is a discrete organ, it performs many different interrelating functions. It becomes essentially evident when abnormalities of the liver occur because many liver functions are distributed simultaneously. Earlier we have learned about some another structure like the exocrine pancreas. Exocrine region of the pancreas. Where is pancreas situated? It lies parallel to and beneath the stomach, and it's a large compound gland, and we have mentioned many major points related to that exocrine pancreas. Now we are learning about the liver. So first we will be learning about the physiological anatomy of the liver and its major functions, and then we will be learning about the jaundice. Although the liver is a discrete organ, it performs many different interrelating functions. This becomes especially evident when abnormalities of the liver occur because many liver functions are distributed simultaneously. This chapter summarizes the different functions of the liver, including filtration and storage of blood, metabolism of carbohydrates, proteins, fats, hormones, and foreign chemicals, formation of bile, storage of vitamins and iron, and the formation of coagulation factors. These are the major functions. So, physiological anatomy of the liver. The liver is the largest organ in the body, contributing about 2% of the local total body weight, or about 1.5 kilogram in an average adult human. The basic functional unit of liver is the liver lobule, which is a cylindrical structure several millimeters in length and 0.8 to 2 mm in diameter. The human liver contains 50,000 to 100,000 individual lobules. The liver lobule is constructed around a central vein that empties into the hepatic veins and then into the vena cava. The lobule is composed principally of many liver cellular plates, two of which are very important, that radiate from the central vein like spokes in a wheel. Each hepatic plate is usually 2 cell thick, and between the adjacent cell lie small bile canaliculi that empty into bile ducts in the fibrous septa, separating the adjacent liver lobules. In the septa are small portal venules that receive their blood mainly from the venous outflow of the gastrointestinal tract by way of the portal vein. From these venules, blood flows into the flat, branching hepatic sinusoids that lie between the hepatic plates and then into the central vein. Thus, the hepatic cells are exposed continuously to portal venous blood. Hepatic arterioles are also present in the interlobular septa. These arterioles supply arterial blood to the spinal tubes between the adjacent lobules, and many of the small arterioles also empty directly into the hepatic sinusoids, most frequently emptying into those located about one-third the distance from the interlobular septa. In addition to the hepatic cells, the venous sinusoids are lined by two other cell types, typical endothelial cells and large Kupffer cells, also called reticuloendothelial cells. Kupffer cells. Kupffer cells are associated with liver, which are resident macrophages that line the sinusoids and are capable of phagocytizing bacteria and other foreign matter in the hepatic sinus blood. The endothelial lining of the sinusoids are extremely large pores, some of which are almost 1 mm in diameter. Beneath this lining, lying between the endothelial cells and the hepatic cells, are narrow tissue spaces called the spaces of Dis, also known as the perisinusoidal spaces. Spaces of Dis, DISSE, or perisinusoidal spaces. The millions of spaces of Dis connects the lymphatic vessels in the interlobular septa. Therefore, excess fluid in the spaces is removed through the lymphatics. Because of the large pores in the endothelium, substances in the plasma move freely into the spaces of Dis. Even large portions of the plasma diffuse freely into these spaces. Basic structure of liver lobule showing the liver cellular plates, the blood vessels, the bile collecting system, the lymph flow system composed of the spaces of Dis and the interlobular lymphatics. Start like bile duct will be there, hepatic artery is there, portal vein will be there, then terminal lymphatics and space of Dis, sinusoids are there, then central vein is there, liver cell plate, Kupffer cell, which performs the function of phagocytizing bacteria, and endothelial cells are there, and bile canaliculi and lymphatic duct will be there. So these are the structures associated with the liver. Next, functions of the liver. Functions as a reservoir of blood cleansing function, metabolic function, secretion of bile, storage functions, role in blood coagulation, catabolic and excretory functions, hepatic vascular and lymph systems. The functions of the hepatic vascular system is described, and the liver function as a blood reservoir. Because the liver is an expandable organ, large quantities of blood can be stored in its blood vessels. Its normal blood volume, including that in both the hepatic veins and the hepatic sinuses, is about 450 ml, or almost 10% of the body's total blood volume. When high pressure in the right atrium causes back pressure in the liver expands, and 0.5 to 1 liter of extra blood is occasionally stored in the hepatic veins and sinuses. The storage of extra blood occurs especially in cases of cardiac failure with peripheral congestion. The liver macrophage system serves a blood cleansing function. Blood flowing through the intestinal capillaries pick up many bacteria from the intestine. Indeed, a sample of blood taken from the portal vein before it enters the liver almost always grows colon bacilli when cultured, whereas growth of colon bacilli from the blood in the systemic circulation is extremely rare. The Kupffer cells, which are the large phagocytic macrophages that line the hepatic venous sinuses, efficiently cleanse blood as it passes through the sinuses. Probably less than 1% of the bacteria entering the portal blood from the intestine succeed in passing through the liver into the systemic circulation. Metabolic functions of the liver. The liver is a large chemically reactant pool of cells that have a high rate of metabolism. These cells share substances and energy from one metabolic system to another, process and synthesize multiple substances that are transported to other areas of the body, and perform myriads of other metabolic functions. In this chapter, we summarize the metabolic functions as especially important in understanding the integrated physiology of the body. So, carbohydrate metabolism. In carbohydrate metabolism, the liver performs the following functions: storage of large amount of glycogen, conversion of galactose and fructose to glucose, gluconeogenesis, formation of many chemical compounds from intermediate products of carbohydrate metabolism. The liver is especially important for maintaining a normal blood glucose concentration. Storage of glycogen allows the liver to remove excess glucose from the blood, store it, and then return it to the blood when the blood glucose concentration begins to fall too low. This is called the glucose buffer function of the liver. Glucose buffer function of the liver. Next is the fat metabolism. Although most cells of the body metabolize fat, certain aspects of fat metabolism occur mainly in the liver. Oxidation of fatty acids to supply energy from other body functions, synthesis of large quantities of cholesterol, phospholipids, and most lipoproteins, synthesis of fat from proteins and carbohydrates to derive energy from neutral fats. The fat is first split into glycerol and fatty acids. The fatty acids are then split by beta oxidation into two carbon acetyl radicals that form acetyl coenzyme A, acetyl CoA, and acetyl CoA can enter the citric acid cycle to be oxidized to liberate tremendous amounts of energy. Beta oxidation can take place in all cells of the body, but it occurs especially rapidly in the hepatic cells. Then, protein metabolism. The body cannot dispense with the liver's contribution to protein metabolism for more than a few days without death ensuing. The most important functions of the liver in protein metabolism are the following: deamination of amino acids, formation of urea for removal of ammonia from the body fluids, formation of plasma proteins, interconversion of various amino acids, and synthesis of other compounds from amino acids. Other metabolic functions of the liver. The liver is a storage site for vitamins. The liver has a particular propensity for storing vitamins and has long been known as an excellent source of certain vitamins in the treatment of patients. The vitamin stored in greatest quantity in the liver is vitamin A, but large quantities of vitamin D and vitamin B12 are normally stored as well. The liver stores iron as ferritin. Except for the iron in the hemoglobin of the blood, by far the greatest proportion of iron in the body is stored in the liver in the form of ferritin. Thus, the apoferritin ferritin system of the liver acts as a blood iron buffer as well as an iron storage medium. The liver forms the blood substance used in coagulation. Substances formed in the liver that are used in the coagulation process include fibrinogen, prothrombin, accelerator globulin, factor 7, and several other important factors. Vitamin K is required by the metabolic process of the liver for the formation of several of these substances, especially prothrombin and factors 7, 8, and 10. In the absence of vitamin K, the concentration of all the substances decrease markedly and almost prevent blood coagulation. The liver removes or excretes drugs, hormones, and other substances. The active chemical medium of the liver is well known for its ability to detoxify or excrete many drugs into the bile, including sulfonamides, penicillin, ampicillin, and erythromycin. Similarly, several of the hormones secreted by the endocrine glands are either chemically altered or excreted by the liver, including thyroxine and essentially all the steroid hormones such as estrogen, cortisol, and aldosterone. Liver damage can lead to excess accumulation of one or more of these hormones in the body fluids and therefore causes overacidity of the hormonal systems. Finally, one of the major routes of excreting calcium from the body is secretion by the liver into the bile, which then passes into the gut and is lost in the feces. So, excess calcium is released like that. When we just look at the liver secretion and the gallbladder emptying, we can see there liver is there, then acid is there in the stomach, pancreas is associated with that, duodenum region, sphincter of Oddi. First, in the liver, bile acids via blood stimulates parenchymal secretion, then vagal stimulation causes weak contraction of gallbladder. Secretin via bloodstream stimulates liver ductal secretion. Bile stored and concentrated up to 15 times in gallbladder. Then cholecystokinin via bloodstream causes gallbladder contraction, relaxation of sphincter of Oddi. So with all these mechanisms, liver secretion and gallbladder emptying happens. Then bile secretion by the liver. One of the many functions of the liver is to secrete bile, normally between 600 and 1000 ml per day. Bile serves two important functions. Bile plays an important role in fat digestion and absorption. Bile is very important in fat digestion and absorption because bile acids in the bile perform two functions. They help to emulsify the large fat particles of the food into many minute particles, the surface of which can then be attacked by lipase enzymes secreted in pancreatic juice. They aid in absorption of digested fat end products through the intestinal mucosal membrane. Then bile serves as a means of excretion of several important waste products from the blood. These waste products include in particular the bilirubin and then product of hemoglobin destruction and excess of cholesterol. Physiological anatomy of biliary secretion. Bile is secreted in two stages by the liver. The initial portion is secreted by the principal functioning cells of the liver, the hepatocytes, which this initial secretion contains large amounts of bile acids, cholesterol, and other organic constituents. It is secreted into the minute bile canaliculi that originate from the hepatic cells. Next, the bile flows in the canaliculi toward the interlobular septa, where the canaliculi empty into terminal bile ducts and then into progressively larger ducts, finally reaching the hepatic duct and common bile duct. From this, the bile either empties directly into the duodenum or is inverted to minutes up to several hours through the cystic duct into the gallbladder. In its course through the bile ducts, a second portion of liver secretion is added to the initial bile in response to secretin, a local hormone. This additional secretion is a watery substance of sodium and bicarbonate ions secreted by epithelial cells that line the ductules and ducts. This second secretion sometimes increases the total quantity of the bile as much as 100%, storing and concentration of bile in the gallbladder. Bile is secreted continuously by the liver cells, but most of it is normally stored in the gallbladder until it is needed in the duodenum. The maximum volume of the gallbladder can hold is only 30 to 60 ml. Nevertheless, as much as 12 hours of bile secretion, usually about 450 ml, can be stored in the gallbladder because water, sodium chloride, and most other small electrolytes are continuously absorbed through the gallbladder mucosa, concentrating the remaining bile constituents and contain the bile salts, cholesterols, lecithin, and bilirubin. Most of this gallbladder reabsorption is caused by active transport of sodium through the gallbladder epithelium, and this transport is followed by secondary absorption of chloride ions, water, and most other diffusible constituents. Bile is normally concentrated in this way about 5-fold, but it can be concentrated up to a maximum of 20-fold. Now, what is the composition of bile? Composition of bile, water is there. Bile salts, bilirubin, cholesterol, fatty acids, lecithin, Na+, K+, Ca2+, Cl-, HCO3-, etc. are the components of bile. when it is first secreted by the liver and then after it has been concentrated in the gallbladder, this concentration is changing. By far the most abundant substance secreted in the bile are bile salts, which account for about one half of the total solutes also in the bile. Also secreted or excreted in large concentrations are bilirubin, cholesterol, lecithin, and usual electrolytes of plasma. Lecithin is there. And cholecystokinin stimulates gallbladder emptying. When food begins to be digested in the upper gastrointestinal tract, the gallbladder begins to empty, especially when fatty foods reach the duodenum about 30 minutes after a meal. The mechanism of gallbladder emptying is rhythmic contractions of the gallbladder wall, but effective emptying also requires simultaneous relaxation of the sphincter of Oddi, which guards the exit of the common bile duct into the duodenum. By far the most potent stimulus for causing the gallbladder contractions is the hormone cholecystokinin. This is the same CCK discussed earlier that causes increased secretions of digestive enzymes by the acinar cells of the pancreas. The stimulus for CCK entry into the blood from the duodenal mucosa is mainly the presence of fatty foods in the duodenum. The gallbladder is also stimulated less strongly by acetylcholine secreting nerve fibers from both the vagi and the intestinal enteric nerve system. Functions of bile salts in fat digestion and absorption. The liver cells synthesize about 6 grams of bile salts daily. The precursor of the bile salts is cholesterol, which is either present in the diet or synthesized in the liver cells during the course of fat metabolism. The cholesterol is first converted to cholic acid or chenodeoxycholic acid in about equal quantities. These acids in turn combine principally with glycine and to a lesser extent with taurine to form glyco and tauro-conjugated bile acids. The salts of these acids, mainly sodium salts, are then secreted in the bile. The bile salts have two important actions in the intestinal tract. Firstly, they have a detergent action on the fat particles in the food. This action, which decreases the surface tension of the particles and allows agitation of the intestinal tract to break the fat globules into minute sizes, is called emulsifying or detergent function of bile salts. Second, and even more important than the emulsifying function, bile salts help in the absorption of fatty acids, monoglycerides, cholesterol, and other lipids from the intestinal tract. They help in this absorption by forming small physical complexes with these lipids. The complexes are called micelles and they are semi-soluble in the chyme because of the electrical charges of the bile salts. The intestinal lipids are ferried in this form to the intestinal mucosa, where they are then absorbed into the blood, as will be described in detail. Without the presence of bile salts in the intestinal tract, up to 40% of the intestinal fats are lost into the feces, and metabolic deficit often develops because of this nutrient loss. Enterohepatic circulation of bile salts. About 94% of the bile salts are reabsorbed into the blood from the small intestine, about one half of this by diffusion through the mucosa in the early portions of the small intestine, and the remainder by an active transport process through the intestinal mucosa in the distal ileum. They then enter the portal blood and pass back to the liver. On reaching the liver and during first passage through the various sinusoids, the salts are absorbed almost entirely back into the hepatic cells and then resecreted into the bile. In this way, about 94% of all the bile salts are recirculated into the bile. So the average of the salts make the entire circuit more 70%, some 70% before being carried out in the feces. The small quantities of bile salts lost into the feces are replaced by new amounts formed continuously by the liver cells. This recirculation of the bile salts is called the enterohepatic circulation of bile salts. The quantity of bile secreted by the liver each day is highly dependent on the availability of bile salts. The greater the quantity of bile salts in the enterohepatic circulation, usually a total of about 2.5 gram. The greater is the rate of bile secretion. Indeed, ingestion of supplemental bile salts can increase bile secretion by several hundred milliliters per day. If a bile fistula empties the bile salts to the exterior for several days to several weeks, so they cannot be reabsorbed from the ileum, the liver increases its production of bile salts from 6-fold to 10-fold, which increases the rate of the bile secretion most of the way back to normal. This demonstrates that the daily rate of liver bile salt secretion is actively controlled by the availability or lack of availability of bile salts in the enterohepatic circulation. Role of secretion and secretin in controlling bile secretion. In addition to the strong stimulating effect of bile acids to cause bile secretion, the hormone secretin that also stimulates pancreatic secretion increase bile secretion, sometimes more than doubling its secretion for several hours after a meal. This increase in secretion consists almost entirely of secretion of a sodium bicarbonate rich watery solution by the epithelial cells of the bile ductules and ducts, and does not represent increased secretion by the liver parenchymal cells themselves. The bicarbonate in turn passes into the small intestine and joins the bicarbonate from the pancreas in neutralizing the hydrochloric acid from the stomach. Thus, the secretin feedback mechanism for neutralizing duodenal acid operates not only through its effects on pancreatic secretion, but also to a lesser extent through its effect on secretion by the liver ductules and ducts. Amount of bile acid return controls rate of synthesis. Bile acid synthesis is happening. Primary bile acids and secondary bile acids will be there. Bile acid synthesized by liver secreted into gut, reabsorbed and recycled through liver with small amount lost in feces. Liver secretion of cholesterol and gallstone formation. Bile salts are formed in the hepatic cells from cholesterol in the blood plasma. In the process of secreting the bile salts, about 1 to 2 gram of cholesterol is removed from the blood plasma and secreted into the bile each day. Cholesterol is almost completely insoluble in pure water, but in bile salts and lecithin, the bile combines physically with the cholesterol to form ultramicroscopic micelles in the form of a colloidal solution. When the bile becomes concentrated in the gallbladder, the bile salts and lecithin becomes concentrated along the cholesterol, which keeps the cholesterol in solution. Under abnormal conditions, the cholesterol may participate in the gallbladder, resulting in the formation of cholesterol gallstones. And the amount of cholesterol in the bile is determined partly by the quantity of fat that the person eats, because liver cells synthesize cholesterol as one of the products of fat metabolism in the body. For this reason, people who consume a high fat diet over a period of years are prone to development of gallstones. Inflammation of the gallbladder epithelium, often resulting from a low grade chronic infection, may also change the absorptive characteristics of the gallbladder mucosa, sometimes allowing excessive absorption of water and bile salts, but leaving behind the cholesterol in the gallbladder in progressively greater concentrations. The cholesterol then begins to precipitate, first forming many small crystals of cholesterol on the surface of the inflamed mucosa, but then progressing to large gallstones. Process of gallstones. Too much absorption of water from bile, too much absorption of bile acids from bile, too much cholesterols in bile, inflammation of epithelium. Then stones are produced: liver, hepatic duct, gallbladder stones, cystic duct, causes, course followed by bile during rest, during digestion. Common bile duct is there, pancreatic duct is associated with that, then sphincter of Oddi, duodenum, papilla of water. Papilla of water. Then bilirubin formation and secretion. Plasma, fragile red blood cells are there. Reticuloendothelial system, heme is produced, heme oxygenase bilirubinin, then unconjugated bilirubin. Liver, in liver it just absorbed bacterial action, conjugated bilirubin bacterial action, urobilinogen, then stercobilinogen, then oxidation, stercobilin, intestinal contents, then urobilinogen, kidneys, urobilinogen, urobilin. Urobilinogen undergoes oxidation to form urobilin. Measurement of bilirubin in the bile as a clinical diagnostic tool. In addition to bile salts, many substances are excreted in the bile and then eliminated in the feces. One of these substances is the greenish-yellow pigment bilirubin, which is a major end product of hemoglobin degradation, as pointed out in the chapter, which is we will be discussing after some time. However, it also provides an exceedingly valuable tool for diagnosing both lymphatic blood diseases and various types of liver diseases. Briefly, when the red blood cells have lived out their lifespan, on average 120 days, and have become too fragile to exist in the circulatory system, their cell membranes rupture and the released hemoglobin is phagocytized by tissue macrophages, also called the reticuloendothelial cells system, through the body. The hemoglobin is first split into globin and heme, and then the heme ring is opened to give a free ion, which is transported to the blood by transferrin and a straight chain of 4 pyrrole nuclei, which is the substrate from which bilirubin will eventually be formed. The first substance formed is biliverdin, but this substance is rapidly reduced into free bilirubin, also called unconjugated bilirubin, which is gradually released from the macrophages into the plasma. This form of bilirubin immediately combines strongly with plasma albumin and is transported in this combination throughout the blood and intestinal fluids. Within hours, the unconjugated bilirubin is absorbed through the hepatic cell membrane. Then passing to the inside of the liver cells, it is released from the plasma albumin and soon thereafter conjugated about 80% of the glucuronic acid to form bilirubin glucuronide, about 10% with sulfate to form bilirubin sulfate, and about 10% with a multitude of other substances. In these forms, the bilirubin is excreted from the hepatocytes by an active transport process into the bile canaliculi and then into the intestine. Formation and fate of urobilinogen. Once in the intestine, about half of the conjugated bilirubin is converted by bacterial action into the substance urobilinogen, which is highly soluble. Some of the urobilinogen is reabsorbed through the intestinal mucosa back into the blood, and most is re-excreted by the liver back into the gut, but about 5% is excreted by the kidneys into the urine. After exposure to air in the urine, the urobilinogen becomes oxidized to urobilin. Alternately, in the feces, it becomes altered and oxidized to form stercobilin. This interrelations of bilirubin and other bilirubin products are very important. Then the next major topic is nothing else but the jaundice, excess of bilirubin in the extracellular fluid. Jaundice refers to a yellowish tint on the body tissues, including yellowness of skin and deep tissues. When we just try to learn jaundice, we need to know some major terms related to this. So first is the bilirubin, that is which we have just mentioned. Bilirubin, yellow breakdown product of heme from hemoglobin. It is responsible for the yellow color of urine and the yellow discoloration in jaundice. Then hemolytic jaundice, an excess of unconjugated bilirubin in the blood due to excessive hemolysis. Obstructive jaundice, an increase in conjugated bilirubin in the blood due to obstruction of biliary flow. Urobilinogen, a colorless product of the reduction of bilirubin by the bacteria in the intestine. It can be reabsorbed from the intestine into the circulation or later excreted by the kidney, constituting an enterohepatic urobilinogen cycle. Van den Berg reaction. Test to measure the concentration of conjugated bilirubin in the blood. Jaundice refers to a yellowish tint to the body tissues, including a yellowness of the skin and deep tissues. The usual cause of jaundice is large quantities of bilirubin in the extracellular fluids, either unconjugated or conjugated bilirubin. The normal plasma concentration of bilirubin, which is almost entirely the unconjugated form, averages 0.5 mg per dl of plasma. In certain abnormal conditions, it can rise to as high as 40 mg per dl, and much of it can become the conjugated type. The skin usually begins to appear jaundiced when the concentration rises to about 3 times normal, that is about 1.5 mg. The common cause of jaundice are increased destruction of red blood cells with rapid release of bilirubin into the blood, and the obstruction of the bile ducts or damage to the liver cells so that even the usual amounts of bilirubin cannot be excreted into the gastrointestinal tract. These two types of jaundice are called respectively hemolytic jaundice and obstructive jaundice. They differ from each other in the following ways. Hemolytic jaundice is caused by hemolysis of red blood cells. In hemolytic jaundice, the excretory function of the liver is not impaired, but red blood cells are hemolyzed so rapidly that the hepatic cells simply cannot excrete the bilirubin as quickly as it is formed. Therefore, the plasma concentration of free bilirubin rises to above normal levels. Likewise, the rate of formation of urobilinogen in the intestine is greatly increased, and much of this is absorbed into the blood and later excreted in the urine. Obstructive jaundice is caused by obstruction of bile ducts or liver disease. In obstructive jaundice, caused either by obstruction of the bile ducts, which most often occurs when a gallstone or cancer blocks the common bile duct, or by damage to the hepatic cells, which occurs in hepatitis, the rate of bilirubin formation is normal, but the bilirubin formed cannot pass from the blood into the intestine. The unconjugated bilirubin still enters the liver cells and becomes conjugated in the usual way. This conjugated bilirubin is then returned to the blood, probably by rupture of the congested bile canaliculi and direct emptying of the bile into the lymph, leaving the liver. This most of the bilirubin in the plasma becomes the conjugated type rather than the unconjugated type. Tests for jaundice. Serum unconjugated bilirubin. Direct Van den Berg test. Serum conjugated bilirubin. Direct Van den Berg test. Urine urobilinogen. Liver function tests. Serum. Alanine transaminase. Aspartate transaminase. Alkaline phosphatase. Gamma glutamyl transpeptidase. Coagulation tests. Prothrombin time, etc. Then diagnostic differences between hemolytic and obstructive jaundice. Chemical laboratory tests can be used to demonstrate between unconjugated and differentiate between unconjugated and conjugated bilirubin in the plasma. In hemolytic jaundice, almost all the bilirubin is in the unconjugated form. In obstructive jaundice, it is mainly in the conjugated form. A test called Van den Berg reaction can be used to differentiate between these two. When there is a total obstruction of bile flow, no bilirubin can reach the intestine to be converted into urobilinogen by bacteria. Therefore, no urobilinogen is reabsorbed into the blood, and none can be excreted by the kidneys into the urine. Consequently, in total obstructive jaundice, tests for urobilinogen in the urine are completely negative. Also, the stools become clay colored owing to the lack of stercobilin and other bile pigments. Another major difference between unconjugated and conjugated bilirubin is that kidneys can excrete small quantities of the highly soluble conjugated bilirubin, but not the albumin-bound unconjugated bilirubin. Therefore, in several severe obstructive jaundice, significant quantities of conjugated bilirubin appear in the urine. This can be demonstrated simply by shaking the urine and observing the form, which turns an intense yellow. This, by understanding the physiology of bilirubin excretion by the liver and by the use of few simple tests, it is often possible to differentiate among multiple types of hemolytic diseases and liver diseases, as well as to determine the severity of the disease. The spleen is the usual site for extravascular or normal hemolysis. Bilirubin formed here is transported as unconjugated bilirubin in the plasma to the liver. In the liver, it is conjugated to form a soluble bilirubin that is excreted into the bile. Note that there is an excessive intravascular hemolysis, such as the hemolytic anemia. Free Hb is present in the plasma, and as a part of it binds to hemoglobin for transport to the liver. The rest circulates as free hemoglobin and can be filtered by the kidney out of the blood as dimer into a urine, which it can precipitate in the renal tubules. Otherwise, methemoglobin is formed, which breaks down to the free heme, which in turn is bound by another plasma protein called a hemopexin, or by albumin to yield methamalbumin. In both the instances, it is transported to the liver, and where a similar chain of events occurs, leading to the formation of bilirubin. So, in the fate of hemoglobin after extravascular or intravascular hemolysis and points at which jaundice can occur, UDP, uridine 5-diphospho-glucuronide transferase. Then spleen is there, extravascular hemolysis, free Hb, heme, biliverdin, bilirubin, unconjugated bilirubin bound in plasma to albumin, liver, UDP, then bilirubin monoglucuronide, bilirubin diglucuronide, excretin, and bile. Blood, extravascular hemolysis, free Hb, methemoglobin, heme, hemopexin, heme, albumin, heme, liver. That is happening in the conjugated bilirubin type.